Welcome to the fourth lecture on graph theory. Today we will learn diameter of a graph and graph isomorphism. So, the diameter of a graph is computed as follows. You compute, given a graph, you compute the distance between every pair of vertices. By distance I mean you compute the length of the shortest path between every pair of vertices, and then once you have the distance between every pair of vertices, the maximum of all these distances is the diameter of the graph. So, I will formally define what is diameter of a graph and give many examples to understand the definition of diameter of a graph. So, let us start with the diameter. Of a graph G. Okay. So, notation for this one is diam G. So, this is the maximum of the distances d u v and u v are from the set V. So, d u v is the distance between vertex u and vertex v. So, this is computed as follows. So, d u v is equal to the length of the shortest path between u and v. Okay. So, I will give an example to illustrate this definition. Let me start with the Petersen graph that we learned in the previous class in lecture 4. So, it has 10 vertices and we know how to construct Petersen graph. So, these are the edges of this graph. And this edge is adjacent to these two edges. Similarly, these two vertices are adjacent and these two vertices are adjacent. So, this is what the Petersen graph is. Petersen graph. Now, I can label them by A, B, C, D, E, F, G, H, I and J. And now you can see that, so what I have to do is that I have to compute the distance between every pair of vertices. Now, the distance between u v when u v are adjacent like B C, the distance between B and C, there are many paths between B and C. You can come to C from B using this path also, like you go to A to E, E to D, D to C, that is a longer path, but you have to consider the shortest path between B and C. So, if this is equal to 1, if U and V are adjacent, and now you consider two vertices, say U and V, and these two vertices U, for two non-adjacent vertices U and V are non-adjacent. So, for example, D and B are two non-adjacent vertices, and there are many paths between D and B. So, for example, this is a path D J H B, this is a path of length 3. There are many other paths from D J G A B, this is a path of length 4, but I have to consider the shortest path. The shortest path is D C B, and this is equal to 2, and this is true for any two non-adjacent vertices. Okay. So, if two vertices are adjacent, and then obviously the distance between those two vertices is equal to 1, and if two vertices are non-adjacent, then their distance is 2, especially for the Petersen graph, because in case of Petersen graph this is true, because every pair of non-adjacent vertices have a common neighbor. In case of Petersen graph, of course. So, what I mean by neighbor, the meaning of neighbor is that so the neighbor of A, vertex A, are E, G and B. So, these are three neighbors of the vertex A. So, if you take any two non-adjacent vertices, for example, D and A, they have a common neighbor. That is why the distance between two non-adjacent vertices is 2. So, you compute the distance between every pair of vertices, and you see that for two vertices which are adjacent, the distance is 1, and for any two vertices, non-adjacent vertices, the distance is equal to 2. So, the diameter of Petersen graph is equal to 2. Okay. So, let me take this is one example. Let me take another example, so that you do not have any doubt. This is called cube. It has 8 vertices. So, I label them by again A, B, C, D, E, F, G, H. Now, you compute the distance between any pair of vertices. For example, the distance between B and D, the distance between B and D is 2. Now, the distance between say D and F, D and F is equal to 3 because this is the shortest path D H E F. There are many paths of length 3. So, this is one, the other one is D A B F. So, the distance is equal to 3. So, this way you can see that the distance between, you can compute distance between every pair of vertices, and you can see that the maximum distance is equal to 3. So, this is denoted by Q3. So, the diameter of Q3 is equal to 3. Next, we prove result, a theorem related to the diameter of graph. If G is a simple graph, then diameter of G greater than equal to 3 implies diameter of G complement less than equal to 3. This is a beautiful result. So, you know what is the complement of a graph. So, the complement given a graph G, we know how to compute complement of that graph. Two vertices are adjacent in the complement graph if and only if they are not adjacent in the original graph G. So, this is what the complement of a graph. Now, we will prove this theorem. Okay. So, when diameter of a graph G is greater than equal to 3, there are non-adjacent vertices U and V in the graph G with no common neighbor. Okay. So, when I say the graph has diameter greater than or equal to 3, that means there exists a pair of vertices U and V such that the distance between these two vertices is greater than or equal to 3. Since the distance is greater than equal to 3, that means there is no common neighbor of these two vertices. If there is a common neighbor of these two vertices, say A, then there could, the shortest path could have been, shortest path between U and V could have been U, A and V. Okay. So, this is what this is the reason why there is no common neighbor between the vertices U and V. Okay. Now, every vertex x in this set V minus except these two vertices U and V, we consider all other vertices. So, every vertex x is adjacent to at most one of u v in G. Okay. So, now we considered we think about the other vertices except u v. So, suppose these are the other vertices and u and v is here. So, this is u, this is v, and we look at the other vertices with respect to the relation of other vertices with u and v. So, there are some set of vertices here and there are some set of vertices here. As we said that, so these are like this could be x, this could be x. So, these are the vertices like other than u and v. So, the statement says that every vertex x is adjacent to at most one of them. So, suppose that these vertices, these are the set of vertices which are adjacent to v only. Okay. And these are the set of vertices which are adjacent to u only. And these are the set of vertices which are neither adjacent to u nor adjacent to v. So, you can see that there is no vertex which is adjacent to both u and v in the graph G. So, this is how the graph G with respect to the relation or adjacency relation with u and v. Now, what will happen in G complement? This is again the vertex u and the vertex v. So, these are the set of vertices which are neither adjacent to u nor adjacent to v in the graph G. These are the set of vertices which are adjacent to say only v. These are the set of vertices which are adjacent to only u in G. Now, in G complement you see that these vertices are neither adjacent to u nor adjacent to v in the graph G. So, they will be adjacent to both u and v in graph G complement, right. This is from the definition of complement of a graph. Now, this set of vertices are adjacent with v in graph G. So, in G complement they will be adjacent to u only. And this set of vertices are adjacent to u in the graph G. So, in G complement they will be adjacent to v only. Now, you consider any pair of vertices from here. Now, we will be able to prove that for every pair of vertices x and y in say v minus u v, there is a path of length at most 3 in G complement. So, if I take a vertex x here and y from this set, then I can see that there is a path from x to y of length 3, that is this is the path. If this is my x, then this is a path of length 3 from x to y. And if both x and y are here, then I can get a path of length 2 like that. So, that is why you take any pair of vertices, there is a path of length at most 3 in G complement. So, the distance between every pair of vertices in G complement is less than or equal to 3. So, the diameter of the graph G complement is less than or equal to 3. Okay. So, next we prove another result related to the diameter of graph, theorem, another theorem. If this is slightly complicated compared to the previous one, if diameter of the graph G is greater than equal to 4, then diameter of G complement is less than or equal to 2. Okay. So, the diameter of a graph G is given to be greater than or equal to 4. That means there exists a pair of vertices, say u and v, such that their distance is 4, and that is why the diameter is 4 or more than 4. Okay. So, the proof of this theorem is since diameter of a graph G is greater than equal to 4, that means there exists a path, there exists a pair of vertices, there exists a pair of vertices u and v in V such that the distance between u and v is greater than or equal to 4. So, I will use the notation, that is the distance between u and v in the graph G, that is what the notation for this one. Again you considered a pair of vertices, suppose x and y are two vertices in V minus u v. So, I am not considering the vertices u v. We need to prove that the distance between any pair of vertices in G complement is less than or equal to 2. In order to prove that, the diameter of G complement is less than equal to 2. Okay. Now, we considered different cases probably. So, case 1. Similarly, we look at the other vertices with respect to their adjacency with u and v, adjacency relation with u and v. So, u and v are two vertices which are at distance 4 or more than 4, and x and y are any two arbitrary vertices. Now, x can't be adjacent to both u and v in G. So, this is the situation in G. If x is adjacent to both u and v, then there is a path of length 2 between u and v in the graph G. Okay. So, but we have but the distance between u and v in the graph G is greater than or equal to 4. So, x can't be adjacent to both u and v. This is one observation. X can be adjacent to only one of them, right. This is one situation. Case 2, again how x and y are related with u and v in terms of the adjacency relation. The other case is that of course, y adjacent to v, only v, that is the same as the case 1. So, this case we will assume that x is not adjacent to u and v. Similarly, y is also not adjacent to u and v. The case 3 is x is here, y is here, and u v are here. X is adjacent to y and y is adjacent to v. So, these are the three cases basically you can think about it. So, we consider 3 cases which cover almost everything, I mean everything, not almost. Now, what else we can assume here is that so this is a possible situation, this is possible, this is possible in G. Now, what else we can assume is that x and y are also adjacent in G. Otherwise, if they are not adjacent in G, they will be adjacent in G complement, and then there will be a path of length 1 between x and y. But what we are trying to prove is that the distance between x and y is less than or equal to 2. So, in case 1, I will assume that x and y are adjacent. In case of case 2 also, I will assume that x and y are adjacent. So, in case 3, I can't assume that x and y are adjacent. If I make x and y adjacent in G, then there will be a path of length 3 in G between u and v, but I have assumed that the distance between u and v is greater than equal to 4 in G. So, in this case what we are assuming is that assume x and u, they are adjacent in G. This is the edge set in the graph G, and y and v are adjacent in G. Now, as I said that this can't be adjacent if x and y are also adjacent in G, then the distance between u and v in the graph G will be 3. Okay. This contradict the assumption that the distance between u and v is greater than equal to 4. Therefore, therefore x and y are not adjacent in graph G, and hence they are adjacent, x and y are adjacent in G complement. Right. So, the distance between x and y in G complement is equal to 1. So, in this case, in case 3 we have proved that the distance between x and y is equal to 1, because this is the situation in graph G. In graph G complement, it will be like this, x and y will be adjacent, because they are not adjacent here. So, in graph G, this will be something like this. Okay. So, we proved that distance between x and y is equal to 1 in G complement. So, here in case 2, this is the situation in G. So, in G complement, of course, this edge also will be there. In G complement, what will happen is that x, y, u, v. So, x is neither adjacent to u nor adjacent to v in G. So, x will be adjacent to u and v both in G complement, and similarly y will be also adjacent to u and v in G complement. So, here in this case, in case 2, we will get a path between x and y in G complement of length 2, and the path is obviously the path is x u y or x v y. Okay. In this case also, in case 1 also, this is G, and in G complement it will be like this, x y u v. So, y is neither adjacent to u nor adjacent to v in G. So, y will be adjacent to u and v in G complement, and x will be adjacent to v, and of course, this will be there. So, in this case also we have distance between x and y is 2 in G complement, because here I can see a path of length 2 between x and y, and here is that path x v y is a path of length 2. So, in this first part of lecture 4, we have learned what is diameter of a graph. So, you can now compute, given any graph, you can compute the diameter of that graph, and we have learned about learned 2 results related to diameter of a graph. Thank you very much.